Namaste. I am Dr. Neeraj Upadhyay, an assistant professor in Department of Chemistry, Dr. Hari Singh Gaur Vishwavidyalaya, and coordinator of this course, again with you for presenting next lecture of our MOOC. The title of this lecture is Free Electron Model and its Application to Electronic Spectra of Polyenes. This lecture is written by Dr. Sumit Kumar and Dr. Rampal Pandey, and I am the presenter. In last two lectures, we learned about origin of color and electronic spectra. We have seen the conjugated pi systems are generally colored. In today's lecture, we will see one of such model which deals with free pi electronic system. Calculating a system other than hydrogen-like without any approximation is very difficult to be done. For system having more than one electron, both approximation and use of computer is needed. Computational chemistry is a branch of chemistry which is used to calculate structure and various properties of molecules. These properties are structure, binding energies, resonance energies, dipole and higher multipole moments, vibrational frequencies, electronic spectra and other spectroscopic quantities. The method used to calculate these properties consume various amount of computational resources depending upon the molecular system, whether it contains one molecule or a group of molecules. These computational methods can range from approximate to accurate depending upon the approximation made at the time of the calculation. Ab initio method is one of the important methods used in computational chemistry to solve Schrödinger equation of a molecule. It describes the wave function or state function of a quantum mechanical system. Ab initio method is entirely based on quantum mechanics and basic physical constants. Ab initio method is difficult to use for macromolecules. Therefore, another important method called semi-empirical methods are developed to treat the macromolecules such as polyenes. The canonical molecular orbitals of planar unsaturated conjugated double bond molecule can be divided into sigma and pi molecular orbitals depending upon sign of reflection of these wave function along the molecular plane. The semi-empirical method treats sigma and pi orbitals differently, and this is due to difference in symmetry between sigma and pi orbitals. Sigma orbital is spherical and has even symmetry along the molecular plane, whereas pi orbital is double dumbbell in shape and has odd symmetry along the molecular plane. Pi electrons has greater polarizability due to pi electrons, which conclude that it is most susceptible to perturbation from chemical reactions. Thus, assumption has been made during the solution of Schrödinger wave equation is that the only pi electron rather than using all the electrons during the calculation will be counted. This simplifies the calculation a lot. You can understand simplifying this complexity by taking simple example like ethylene. So, how many pi electrons are there for ethylene? It's only 2. Okay. So, what is the total number of electrons involved in the molecule? 1 electron is contained each by hydrogen and 6 electrons are contained by each carbon. We have 4 such hydrogens and 2 such carbons. This makes involvement of total 4 plus 12 means 16 electrons. So, without any approximation, the calculation is needed to be done for 16 electrons. But once we move to an approximation that only pi electron will be counted, the calculation gets simplified and is needed to be done for 2 electron system only. Similarly, another example is butadiene, which has only 4 pi electrons but 30 electrons in total. So, you can understand how this method is useful in simplifying the calculation. Thus, accountability of only pi electrons in the calculation surely simplifies the procedure of calculation and at the same time look convincing, as only pi electrons are free to move over the sigma bonded skeleton of conjugated molecules. Further, free electron molecular orbital method is used to explain electronic spectra of pollen. Free electron molecular orbital method is a simple method but has shown a great success to explain the absorption maxima for pollen having conjugated double bonds. The variation in absorption maxima has also been explained for the chains as per its chain length. The free electron wave function provides a graphical representation of the corresponding molecular orbitals. Such pi electrons are considered as free electrons. It has been suggested that the pi electron of the ring move freely along the chain having conjugated double bonds. In an approximation, the field, that is potential field, will be always constant in this limit. Particle in one-dimensional box model provides a quantum mechanical approximation for free movement of a particle inside a one dimension well having impenetrable barriers. Further, the extension to three-dimensional picture of particle in a box model is much useful for understanding the electronic spectra of pollen. This hypothetical classical model can be illustrated to quantum system. In this classical model, a particle is trapped inside a box having large boundaries, but the particle is free and hence likely to be found at one place than the other. When the length of the box becomes smaller on the scale of a few nanometer, the quantum mechanical effect comes into the picture. Interestingly, this problem can be solved analytically without taking any approximation. Figure on your screen shows a schematic diagram for the particle in a box model in one dimension. The potential outside the box is infinitely large and interior of the box has a constant zero potential. It implies that there is no interaction between particle present inside the box and at the same time the particle is repelled back from the walls if the particle comes closer to that wall. Mathematically, Vx is equal to limit infinity to 0, 0 to x to L, where L is the length of the box. The solution of this model shows that particle can never be found at certain points called spatial nodes. The state of lowest energy is called ground state, whereas state of higher than ground state is excited states. The detailed solution you have already learnt in this course. So, let us not go into detail of the calculation, better talk about the solutions. Solution of Schrodinger equation within the box implies that energy E of nth state En is equal to n square h square divided by 8 MEL square, where n is equal to 1, 2, 3, etc. N is the different energy levels, h is Planck's constant, me is the mass of the electron and L is the path length. And the wave function of particle in a box at nth state is psi n equal to root under 2 by L sin n pi x by L. The interpretation of results shows that the number of spatial nodes increases as n increases and number of nodes is n minus 1 for psi n wave function of particle. Free electron molecular orbital is simplest semi-empirical pi electron model. Here the inter-electronic repulsion is neglected and pi electron is considered as in the particle inside the box, where potential in the box is either 0 or certain region within the box and infinite for outside the region. As the interelectronic repulsion is neglected, the Hamiltonian for pi electron is S psi equal to E psi. Here, the overall Hamiltonian takes the account of each pi electrons associated in the molecular chain. We are just introducing the background of free electron molecular orbital theory, and some terminology may become difficult for you. We will include that in glossary at the end of the lecture. For not breaking any flow of the lecture, we are just continuing with those terms only. Interested students can learn that from the glossaries only. The wave function of pi electron is generated as antisymmetric product of wave function using Slater determinant of spin orbitals. The spin orbital for each electron has been constructed following Pauli's principle. We have already learned that the Pauli principle says that within a system, two or more identical fermions, that is particle with half integer spins such as electrons, cannot occupy same quantum state such as spin orbital. A spin orbital is defined as a product of one electron spin function and one electron orbitals. Interestingly, the Hamiltonian of pi electrons in the core does not involve spin. Therefore, the contribution of spin function to its wave function can be ignored. The free electron molecular orbital approximation says that the conjugated chain molecule can be considered as one-dimensional box along the molecular plane, and a free electron can be considered as an electron inside a one-dimensional box. Thus, the associated energy E can be calculated for each molecule using the equation En equal to n square h square divided by 8 MEL square, where n is equal to 1, 2, 3, as you know, we have already discussed in past. The filling of the pi electron in each energy level is restricted by Pauli's principle, and so the total electrons fill half n lowest energy states. Means if n is the total energy state, the total electron that fills in molecular orbital is in the half of the orbitals. Then energy required for the transition from nth state to n plus 1th state is En plus 1 minus En is equal to n plus 1 square h square divided by 8 MEL square minus n square h square divided by 8 MEL square. That will make a value 2n plus 1 into h square divided by 8 MEL square. Now, let us talk about electronic spectra of Polyenes. Free electron molecular orbital can be used in the discussion on the electronic spectra of Polyenes. Let us suppose these are n number of pi electrons in the conjugated double bonded Polyenes. For example, 2 pi electrons in case of ethene fill the lowest molecular orbitals. Hence, the highest occupied molecular orbital corresponds to n equal to 1, and the lowest unoccupied molecular orbital corresponds n equal to 2. Therefore, a low energy or low frequency transition happens from n equal to 1 to n equal to 2 as per the selection rule delta n equal to 1 for a particle in a box. You can see the figure on your screen. In general, for n pi electrons, the total number of occupied free electron orbital is n by 2. Thus, the longest wavelength for the transition is calculated from the equation hc by lambda is equal to E n by 2 plus 1 minus E n by 2. The energy associated in a particle in a box applied here. So, hc by lambda is equal to n by 2 plus 1 square h square divided by 8 MEL square minus n by 2 whole square h square 8 MEL square, that becomes 1 by lambda is equal to h by 8 MECL square into n plus 1. This makes equation 4. Thus, the free electron molecular orbital method is used for the estimation of the electronic spectra of conjugated polyenes. For example, 1,3-butadiene. Here, L1 and L2 are the bond lengths of single and double bond respectively. On applying the free electron molecular orbitals to polyenes having conjugate double bond, pi electrons do not restrict to the molecule, and therefore an extra length of 3/4 L1 plus 1/4 L2 has been added to each, and eventually 3/2 L1 plus half L2 added to the bond length of the polyene. So, this makes L equal to mL1 plus m plus 1 into L2 plus 3/2 into L1 plus half L2, that is, it becomes m plus 3/2 into L1 plus L2. If m is the number of carbon in the polymeric chain, this equation becomes L equal to half into n plus 1 into L1 plus L2, keeping the value of bond length in equation 4, where the number of carbon atom is equal to the number of pi electrons. Therefore, lambda becomes 2 me Ch inverse L1 plus L2 square into n plus 1. This provides an idea about the longest wavelength for transition for highest occupied molecular orbital to lowest unoccupied molecular orbital in case of polyene. Let us look at some examples with some more clarifications. Let us talk about butadiene first. Butadiene lies in two conformers, the trans conformer and the cis conformer, where S denotes the conformation along the single bond. These are shown in figure on your screen. The UV, IR and Raman spectroscopy studies along the quantum calculation conclude that the S trans is predominantly available compared to S cis conformers. Butadiene in 96% cases exists in trans form. It has 4 pi electrons and it is treated as independent particle in a box. The 2 occupied and 2 unoccupied orbitals have been depicted in the figure shown in your screen. The longest wavelength during transition relates with transition from highest occupied molecular orbital to lowest unoccupied molecular orbital, that is n equal to 2 to n equal to 3. This is calculated from equation 4 and this becomes 1 by lambda is equal to 3h divided by 8 me Cl square, and the energy required for the transition from highest occupied molecular orbital to lowest unoccupied molecular orbital is calculating using equation 3. Figure on your screen show the wave function of 4 occupied or unoccupied orbital corresponding to various states assuming the particle in a box model. These wave functions are sine functions having the same amplitude but different wavelengths. The increase of wavelength leads to a sharper curvature and therefore has an increase in the kinetic energy of the particle of such electrons. The increase in nth state increases the number of nodes. Psi 1, psi 2, psi 3 and psi 4 have 0, 1, 2 and 3 nodes respectively. A conjugated double bonded network having pi electron move in the pi orbitals of polyene. Therefore, the movement of electron taken along the delocalized chain and the length of the polyene is taken as length L of the box. The bond length between carbon-carbon is RCC. The length of polyene having Nc carbon atom becomes L equal to Nc minus 1 into RCC from. For nth state, En equal to V0 plus n square h square divided by 8 me L square, if V0 is the potential inside the box. The individual wave function for the orbital in such case psi n is equal to root under 2L sin n pi Lx by L equal to root under 2 by L sin n pi into Nc minus 1 RCC divided by L, where Lx denotes the length of the box along the molecular plane and Lx is equal to Nc minus 1 into RCC. The wave function of same sign are additive and enhance amplitude of the wave function, while wave function of different sign create nodes and hence shown anti-bonding interaction. A conjugated network system having 9 centers, that in case of 1357 non-alternate radical has been shown in your screen. The Polyene radical has 9 electrons which completely fill 4 orbitals having lowest energy and partially fill 5th orbital. Figure on your screen shows the wave function of these orbitals, which are sine function having same amplitude and of various wavelengths. So, the total energy including kinetic and potential energy has been calculated by adding energy of individual electrons. The energy associated to the electronic configuration change due to excitation of one electron are delta E 4 to 5 is equal to 5 square h square divided by 8 me L square minus 4 square h square divided by 8 me L square. This becomes h square by 8 me L square into 5 square minus 4 square. Similarly, delta E 5 to 6 is equal to 6 square h square divided by 8 me L square minus 5 square h square divided by 8 me L square. This becomes h square 8 me L square into 6 square minus 5 square. The above results provide a qualitative picture of the 2 pi to pi star transitions, and color of the molecule depend upon the color of the complementary color of the light absorbed. Further, the energy of lowest state also changes with the length of the molecule, as the square of length is in the denominator. Now, let us summarize all the findings. Computational method is useful to determine several properties of molecules and solids such as structure, binding energies, resonance energy, dipoles and higher multiple moments, vibrational frequencies, electronic spectra and other spectroscopic quantities. The free electron molecular orbital method explains absorption maxima for polyene having conjugated double bond and depends on chain length. Pi electron of the ring move freely along the chain having conjugated double bond in an approximately constant potential field, and those electron is considered as free electrons. Free electron molecular orbital method assumes that the inter-electronic repulsion is negligible and the pi electron is considered as the particle in a box, where potential in the box is either 0 within the box and infinity for outside the box. Particle in a box solved the Schrodinger equation and found that energy E of the nth state is equal to n square h square divided by 8 me L square. Here n may become 1, 2, 3 etc. and wave function of the particle in the box is equal to root under 2 by L sin n pi x by L. Free electron molecular orbital method is useful for the determination of electronic spectra of polyenes, and the wavelength obtained is 1 by lambda is equal to h by 8 me Cl square into n plus 1. From the next lecture, we will start photochemistry. So, keep watching, keep learning. Thank you very much for listening this module. Thanks a lot.